So today's lesson looks at a review from last year, entire and mixed radicals. So you are watching this because I'm not here today, and what I've done is I've recorded the lesson as I go through the examples, and I'm also leaving behind a couple of note pages so that if you can't see the screen, you'll be able to copy the notes down. So if we review quickly from previous math classes, square roots. A square root is a number that when multiplied by itself gives me a perfect square. So the square root of 9 becomes 3 because when I take 3 and multiply it by itself, I get 9. If I take negative 3 and multiply it by itself, I also get 9. So I can say that the square root of 9 is both a positive 3 and a negative 3. Or the square root of 16 is a positive 4 and the negative 4. Most of the time, we only usually ever deal with the positive or the principal square root. This is my symbol for a square root. There's no number, it's just the radical sign. Square roots, you have one of two types. You either have rational numbers, meaning it's a perfect square number. It could be a whole number like 16, or it could be a decimal number. The square root of 2.25 equals 1.5. That would also be a perfect square. Then we have non-perfect squares, such as the square root of 17. That's an irrational number. So if we were trying to determine the square root of 17, we could write it out in exact form as the square root of 17 and the negative square root of 17. Or we could change that into a decimal, which would be 4 point something. Cubed roots are the same as square roots, but instead of multiplying a number by itself twice, we multiply it by itself 3 times. So if I take the number 8 and I take the cubed root of it, I get 2, because 2 times 2 times 2 equals 8. Cubed roots only have 1. So if I'm taking the cubed root of a number, I'm only going to get one possible answer. And that's because if I take 2 and multiply it by itself 3 times, I get positive 8. If I take negative 2 and multiply it by itself 3 times, I get a negative 8. So the other difference with cubed roots is I can take the cubed root of a negative number. I cannot take the square root of a negative number because there's no way I can multiply a number by itself and get a negative result. Because in order to get a negative, I'd have to have a negative and a positive number multiplied together. So the difference between the symbol is the symbol for a cubed root has a little 3 in this spot here, which we call the index. There are other roots, such as the fourth root. So the fourth root of a number is a number that when I multiply it by itself 4 times, I would get that result. So the fourth root of 16, a number that I multiply by itself 4 times to get 16, could be a positive 2, or it could be a negative 2, because every time I multiply it twice, I get a positive. There's my negative, and now I'm back to a positive. So I can write that the fourth root of 16 is a positive or a negative 2. And then I can always find the fifth root. So the fifth root of a number, the fifth root of negative 32, is negative 2. To find this on your calculator, to find like third roots, cubed roots, fourth roots, fifth roots, we press the math button, which brings us to a screen, and then choice number 4, I believe, is a 3 with a radical symbol. And then choice number 5 is an X with a radical symbol. So this X is if I'm trying to find the fourth and the fifth root. And the way that I do that on my calculator, if I wanted to find the fifth root of 32, I would press the 5 first, then that X root button, negative 32, and then my enter. Okay? So class example number 1 asks us to do this without technology. So this is checking your mental math skills. Square root of 64, a positive or a negative 8. Okay? Generally, we're only dealing with our positives, so if you just wrote down positive 8, that would still work. B, the square root of negative 64. Can't square root a negative number. This is not possible at this time. In university level math courses, we do deal with the square root of negative numbers, but we don't deal with them right now. The cubed root of negative 64, a number multiplied by itself 3 times, it's going to give me 64. This negative means it's going to be a negative answer. So if I take 2 and multiply it by itself 3 times, I get 8. So 2 is not going to work. 3 times 3 is 9, times 3 is 27, that didn't work. 4 times 4 is 16, times 4 gives me 64. So negative 64 becomes my answer. D, the 5th root of 1 over 32. If you want to, split it up. The 5th root of 1 over the 5th root of 32. The 5th root of 1 will be 1. In fact, the square root, the cubed root, the 4th root, the 5th root, the 28th root of 1 will always be 1. The 5th root of 32 is going to be positive 2. That was a negative 2. This one would be a positive 2. 4th root of negative 16, not possible. Again, it's not possible because I'd have to multiply a number by itself 4 times to get that negative, and it's not possible to get a negative value. And finally, 10 times the cubed root of 125. So if this was, oh, that should be a negative 4 there. If the cubed root of 64 was 4, the cubed root of 125 has to be bigger than 4. So go up 1 from 4, 5. 5 times 5 is 25. 25 times 5 is 125. So this would become 10 times 5 for a final answer of 50. So at the top of the next page is looking at the root x feature of a calculator. So the 4th root, the 5th root. So what I want you to do is practice this step here on your calculator, and then I want you to practice class example number 2 and 3 on your own. Give yourself about 5 minutes, and then you can press play again, and all the answers will be up on the screen. So if we go through these answers, the 5th root of 243 is 3. The 7th root of negative 16,384 is negative 4. And the cubed root of 125 over 216 would be 5 over 6. If you put this in your calculator as it stands, be careful, you might need to put brackets. I can't remember if the calculator manually puts bracket or automatically puts brackets in. You might have to manually put them in. The other thing to recognize is this is the same as the cubed root of 125 over the cubed root of 216. If we look at class example number 3, this is evaluating to the nearest hundredth. So the 5th root of 500, 3.47. The 6th root of 6/10 is 92 hundredths. And 2/5 times the 4th root of 100 gives me 1/26 hundredths. So all of these numbers are considered to be radicals. So when I use this symbol, this little check mark with a bar over its symbol, this is a radical symbol. So in a radical symbol, we have the index. This tells me the root, the square root, cubed root, 4th root, 5th root, etc. This is basically telling me that I'm going to take this number and break it into something that when I multiply it by itself 3 times or 4 times or n times, I will get 29. So in addition to the index, we have the radicand, which is what appears underneath the radical symbol, and the whole thing together we call a radical. So the other thing too is my index will always be a natural number, so I can't find the 1.2 root of a number. I can find the 2nd root, the 3rd root, the 4th root, but I can't find the 3.5 root. Other things to note, if the index is even, the radicand has to be positive. So I can find the 4th root of 15, but I can't find the 4th root of negative 15. But I could find the 3rd root of a negative number. I could find the 5th root of a negative number. If there is no index, it is assumed that it is an index of 2. So last year we did look at combining radicals, and what we learned is that I can multiply radicals together. So the square root of 9 times the square root of 4 is the same thing as the square root of 9 times 4. And the same thing for division. I cannot do it for adding and subtracting, and we did examples of this last year. So I'm not going to spend a lot of time doing it this year. However, if I look at class example number 4, it says state whether each statement is true or false. I'm multiplying, so the square root of 3 times the square root of 15, square root of 3 times the square root of 5. 3 times 5 is 15. This would actually be true. The square root of 30 divided by the square root of 10, I can divide these two numbers without the radical signs. 30 divided by 10 is 3. This would also be true. In the last one, the square root of 16 plus 9 is not equal to the square root of 16 plus the square root of 9. This would actually be false. And if I were to calculate this out, the square root of 16 is 4, the square root of 3 is 9. This gives me an answer of 25, which the square root of 25 is 5. And we can see that 5 would not be equal to 7. So what I would like you to do right now is take another couple of minutes and look at questions 1, 2, and 5 and practice those. And then when you're ready to move on, go into the next part of the lesson. So the next part of this lesson looks at entire and mixed radicals, which again we also looked at last year. So if I use my calculator, and you can pause right now if you want, I want you to calculate what the values of these three radical combinations are. So if I were to take my calculator and if I was to type in the square root of 96, I would get 9.79796. So to 5 decimal places, the last digit would be a 6. If I then took my calculator and went to root 24, this is what I get. And then if I went 4 times the square root of 6, this is what I would get. So what you should notice is that the answers are all the same. Which means that the square root of 96 is the same as the square root of 2 root 24 and is the same as 4 root 6. These three radicals are the same value. So to explain why they're equivalent, let's start off with the square root of 96. I can write the square root of 96 as a product of two radicals, 4 times 24. 4 is a perfect square. I can take the square root of it. So the first thing is I can separate these two products, write them separately. Square root of 4 becomes 2, and I get 2 root 24. With 96, I can also write it as the square root of 16 times 6. 16 is also a perfect square. So square root of 16 is 4. I get 4 root 6. So the square root of 96 is called an entire radical because the entire thing is underneath the radical symbol. Whereas 2 root 24 and 4 root 6 would be mixed radicals. Kind of like a mixed number when we're talking about fractions. We have improper fractions and we have mixed numbers. Well, we have entire radicals and mixed radicals. Within our mixed radicals, 4 root 6 would be considered a simplified mixed radical. It's in its simplest form, and we know it's in its simplest form because if I look at that radicand does not have a perfect square in it. So the top of the next page just goes through definitions of pure and mixed radicals. And so now if we look at conversion. If I want to go to an entire radical and I want to change it to a mixed radical, what I'm looking for is I'm looking for perfect square numbers that are factors of that radicand. So on the sideboard in the red and the green, I do have the list of perfect squares and perfect cubed numbers. So if I look at 72, I look at my sideboard and I ask, what can I divide 72 by? And we're given the prompt. 72 can be written as 2 times something. 2 times 36. 36 is a perfect square. When I take the square root of 36, I get 6. So I can state that 72 can be written as 6 root 2. The thing that I want you to realize with this is I don't have to choose 36. If I had looked at 72 and right away said, oh, I can multiply it by 9. 9 times 8. Square root of 9, that's my perfect square. That's my 3. So now I have 3 root 8. Oh, wait, I can divide 8 by 4. So now instead of 8, I have 4 times 2. 4 being another perfect square number. Square root of 4 is 2. 3 times 2 gives me my 6. So I could do this in more than one step. I don't have to find the largest perfect square, but I need to make sure that if I take a perfect square out, I'm not left with another perfect square factor in what remains. If I am looking at cubed roots, now I'm looking for perfect cubed numbers. So 108, again, they've got the prompt in there that I can divide 108, can be written as 4 times something, would be 4 times 27. The cubed root of 27 is 3. So then what I have is that the cubed root of 108 I can write as 3 times the cubed root of 4. Please make sure that you write this as an actual index. It should be smaller and it should be written in the hook of the radical symbol. If I have an index greater than 3, if I had a 4th root or a 5th root, it would be the same thing. I'd be looking for a perfect 4th power, a perfect 5th power number. So if we look at class example number 5, I'm actually only going to do A, B, and D because our curriculum, we don't have to do the 5th powers. So if I look at 320, I'm trying to divide 320 by a perfect square. So I know I can divide this by 4 because I know I can divide 32 by 4. If I can divide it by 4, I'm going to check whether or not I can divide it by 16, just because 4 and 16 have that relationship. If I take 320 and divide it by 16, I get 20. So it works. It's still a fairly big number that I'm left with. So if I can go 4 and I can go 16, I'm going to try 64. And when I do 64, I get 64 times 5. Now, I usually skip this step in here because what I always do is I always put my perfect square first. Square root of 64 is 8, and then I'm left with my root 5. Cubed root of 6,000, so I'm looking for my perfect cube numbers. If I look over on the side wall at my green numbers, I see 1,000 is in there. So I can write this as 1,000 times 6. The cubed root of 1,000 is 10. And I get 10 times the cubed root of 6. Double check, I look at my list. Is 6 on that perfect cube list? It's not, so then I can go on. And the last one, 2 times the cubed root of negative 40. Again, I look at my list. Can I divide 40 by one of those perfect cube numbers? I can. I can divide it by 8. So I get 2 times the cubed root of negative 8 times 5. If I take the cubed root of negative 8, I get negative 2. And if I take negative 2 and I multiply it by 2, I get negative 4. Cubed root of 5. Now, because we're talking about a negative factor here, this could have also been the cubed root of 8 times negative 5, in which case my final answer would have been 4 times the cubed root of negative 5. Either one would have been acceptable. There's not one that would be more right than the other. I would allow either answer to stand. So let's look at an application question. We're going to look at Pythagoras' theorem because Pythagoras' theorem has radicals in it. So it says determine the exact length of the line segment in simplest radical form using the theorem and then using the distance formula. So if I use the Pythagoras theorem, which is a squared plus b squared equals c squared, that means that I'm making a triangle. This becomes my C, and then my A and B, doesn't really matter which one is which. I can label them either way. So the length of my A column is 3, and my B horizontal, 3, 6, 9. So I get 9 plus 81, which is 90. So then C would equal the square root of 90. That's the exact length of it. If I put that in my calculator gives me some decimal answer. That's no longer the exact length. Within this square root of 90, I then have to see, could I write this as a mixed radical? So I look at my perfect square list. I can divide 90 by 9, so I can rewrite this as 9 times 10. Square root of 9 becomes 3, and I have 3 root 10 as a final answer. If I use my distance formula says I find the difference of the x values and I square it. So 3 minus negative 6. And then I add that to the difference in my y values. 1 minus negative 2. And I will square that. So 3 minus negative 6 is a positive 9. So 9 squared. 1 minus negative 2, 3 squared. So now I have 81 and 9 again. I still end up with the same answer. So I still get the square root of 90, which is still going to end up simplifying, to be 3 times the square root of 10. So now again, pausing to do question 6, A, D, E, F, 7, and then 9, A, C. And then you're going to look at converting mixed radicals to entire radicals. So the final part of this lesson is going from a mixed radical to an entire radical. So if I can go from an entire to a mixed, I should be able to go from a mixed to an entire. So what you need to remember is, what does the index tell us? The index tells us how many times we would have to multiply a number together to get what's underneath the radical symbol. So if I have a 3 on the outside of the radical symbol and I'm putting it underneath where it's a square root, that means that I'd have to multiply that 3 by itself twice. Or I'd have to square it. So if I take the 3 and I square it, I get 9. 9 times 3 is 63. So then I get 3 root 7 equals the square root of 63. If I have fractions, I would do the exact same thing. So in this case here, I have a cubed root. So if I am trying to take the cubed root of 160 times 1/2, to move that 1/2 underneath the radical symbol, I would cube it. So if I cube it, treat the top and the bottom separately. So I'd take the 1 and I would cube it, which would give me 1. Take the 2 and cube it, and that would give me 8. And if I take 1/8 of 160, I get 20. So I get that the cubed root of 20 is equal to 1/2 times the cubed root of 160. So take a moment with class example number 7 and see if you can do these 5 questions. Give yourself a couple of minutes and then you can press play again and see how I go through these questions. So if we look at A, if I want to put the 2 underneath the radical symbol, I square it and I multiply it by that existing radicand of 3. Well, I guess I should square it and not cube it. If I square 2, I get 4. 4 times 3, I get 12 for an answer. With B, I have a negative 5 times the square root of 6. Now, the question to ask, if I put that negative 5 underneath the radical symbol and I square it, I'm going to get a positive number. And then if I tried to work from the bottom up to the top, there'd be no way of getting that negative again. So when I'm dealing with a square root, a 4th root, a 6th root, or an even number, even index, the negative stays outside the radical. Because if I put it inside, there's no way to get it back out again. Take the 5 and I square it. So that becomes 25 times 6. And I get the square root of 150, or the negative square root of 150. With C, because the negative is the negative 4 would be to the power of 3. Because it's an odd index, I can take that negative 4 and I can cube it underneath the radical. So negative 4 cubed is negative 64, which when I multiply it by 6 gives me negative 384. And I need to remember to put my index of 3. D, we're dealing with a 4th power. So when I go to put that 5 underneath the radical symbol, I'd have to raise it to the power of 4. So if I raise it to the power of 4, I'm going to get 625 times 2, and that'll give me 1250, the 4th root of 1250. And then the last one, we're dealing with a fraction. So it's a cubed root. It would be 4/5 cubed times 100. So 4/5 cubed is 4 cubed, which is 64, over 5 cubed, which is 125. And here's something neat that I can do. 125 can each be divided by 25. So I get 5 here and 4 there. So if I take 64 and I multiply it by 4, I would get 256 over 5. Okay. Class example number 8 says, without using a calculator, arrange the following mixed radicals in order from greatest to least. In order to do this, the best way to do this, convert them all into entire radicals. Because if I was to put radicals on a number line and say this is 0 and this is 10, well, the square root of 81 is 9. The square root of 64 is 8. So if I compare just entire radicals, the bigger the radical is, the bigger the number is going to be. So I can convert all of these into entire radicals, and then I am better able to organize them from greatest to least. So if we take the 3√6, take the 3 and square it, becomes 9, and I get 54. If I have 6√3, I take the 6 and I square it, so I get 36 times 3, which is 108. 18 is already done for us, so now I'm at 2√7. Take the 2 and square it gives me 4. So now I have the square root of 28. And the last one, take 7 and square it, becomes 49 times 2, and I get 98. So now when I go to put these in order, greatest to least, the biggest radical is 108, which was 6 root 3, because I go to their original, the original way that they were written. After 108, 98, so that's 7 root 2. 54 becomes 3 root 6. 28 is 2 root 7. And root 18 is at the very end. So to add to the last part of the questions, 10, A, B, E, F, 12, 14, and 15. And that is it for lesson number 1.